Hello and welcome back to the Dragonfly Daily. I am your host, Mike Marsh. I am the product manager of Dragonfly at ORS. You can follow me at Dragonfly Wizard on Twitter. This is going to be lesson 37 in the series. If you want to watch the other episodes in the series, actually, this is lesson 38 in the Dragonfly Daily series. If you want to catch the other episodes, you can go to orss.ca/ytp2, and that'll take you directly to the YouTube playlist for all of the Dragonfly Dailies on the YouTube channel. But while you're there, subscribe to the YouTube channel. As a matter of fact, if you're watching this episode on YouTube, this is lesson 38 in Watershed Transforms. If you are watching it on YouTube, hit the subscribe button right now, and that way you'll be engaged and know when new videos are being posted to the Dragonfly channel. So lesson 38 will be on Watershed Transform. I will be using Dragonfly 2020.1, the second release candidate, so 2020.1 RC2, and we'll be using that for our work today. So if you want to follow along and repeat the exercises, you can. I'm going to switch over to Dragonfly. I'm going to be using the dry sandpack data that we've used in multiple lessons. I haven't actually documented where this data came from in this video yet, so let me show you. I'm going to pop over, open up a tab in my web browser. I'm going to go to Digital Rocks portal, and here on the Digital Rocks portal website, you can browse the data, browse published projects. I'm going to scroll down. If I knew what I was looking for, I would click on the hydrate-bearing sand, and so I have trouble finding it sometimes. I'm just going to do a search for hydrate. And here it is, hydrate-bearing sand from Shangyu Chen and collaborators. So Masha Pradanovic, the whole brain behind Digital Rocks Portal, is one of the collaborators on this data set. In this data set, you'll find multiple image channels, and one of the image channels is the dry sandpack saturated with air. So these are the images that I have loaded in Dragonfly right now. I'm going to go back over to Dragonfly. What we're interested in doing, of course, in analyzing our images is maybe segmenting the individual grains so we could compute grain size or volume distributions or aspect ratio distributions. In doing that segmentation and that labeling of grains, we could rely on the Watershed Transform, which is why we're going to look at this data set today. Now, this is an example of what the labeled grains might look like. I'm actually going to delete that. That's sort of what we're working towards today. But we're going to start with the dry sandpack data. And in fact, to make all of the Watershed Transforms computationally tractable in a minimal amount of time, I'm actually going to crop the data and work on a cropped version of the data. So what I have here is I have the clip box open, but if I right click and go to Modify and Transform Crop, I have the dataset cropper open. And what I've done here is I have set a Z extent from 500 to 699. So that's these 200 slices right in the middle. And I will tell it to apply without create new. So now I'll have just a cropped version of the dataset to work on. So now I have this smaller version of the data and we can get to work. Now, the Watershed Transform is a mathematical morphology tool described quite some time ago, and it helps you perform segmentation, and it can help you perform other tasks. So we will be using the Watershed Transform to apply segmentation. We'll be segmenting bright white grains in the foreground from the dark black air of the background. This will enable us to perform segmentation in a slightly more objective way than some of the other tools. Now, what we need to do to perform a watershed is we have to have markers or seeds, and I'm going to show you how we're going to do that first by creating the markers, and then we'll talk about what's going on in the watershed, and we'll look at some diagrams to discuss that. In order to get started, I want to label the middle of the grains. I want to label the middle of the air, and I can do that just with simple thresholding operations. So if I come over to the ROI tools and I click on Define Range, what we're going to do in creating the seeds, we'll start by clicking on Upper Otsu. We see that this has labeled the foreground pixels. We don't want to label all of the pixels in the grains. We're going to see why in a few minutes, but I'm going to adjust so that I have maybe mostly these high intensity pixels which are in the center of the grains. I'm going to click Add to New to create a region of interest. Then I'm going to do the same thing, but I'm going to reset and choose Lower Otsu. I'm going to have most of the air pixels, and again I'm going to get the pixels in the center of the air, but maybe not all the edge pixels, and I'll click Add to New again. Now I have two regions of interest. I'm going to label the air pixels, let's just call it background, even though it's misspelled. Maybe I'll fix that, background, and I'll give that a dark blue. And I'll label the foreground my grains, and I'll give that a bright orange color. All right, we have these two. Now, the Watershed Transform executes on a multi-ROY, so I'm actually going to select both of these. I'm going to control-click to select the second one. I'm going to choose Create Multi-ROY from ROYs. Now I have this multi-ROY, which as you can see, it has my background and my grains. This is the object that I will perform a Watershed Transform on. But you will note very shortly that I have to have a landscape function. I'm going to define that in a minute. But what I'm going to do is I'm going to take my gray image, my dry sand pack. I'm going to go into Workflows Image Filtering. Here I can create a Sobel, S-O-B-E-L, and I'm going to apply a 3D Sobel and hit Apply. This is going to give me the Sobel filtered version of the image. Now, that'll probably take 5 to 15 seconds to compute. It's already done. We'll do close image processing. And if I look here, I now have, I'm going to go ahead and hide the multi-ROYs. I have this edge map that is the Sobel compared to the map of the grains. Now, what we're going to do now is we're going to switch over to my web browser, and in my web browser, I currently have loaded the page for the hydrite-bearing sand, but I also have a tab open. If you go to Google Images and you type Watershed Transform, you'll see something like this. And this diagram is helpful. We can look at any one of these images. We can look at this image. This is a one-dimensional lesson or a one-dimensional figure illustrating how the Watershed Transform works. What happens is if you have an image intensity function that looks like this, where there are valleys and peaks, you can create markers. So here you see marker 1, marker 2, and marker 3 in this one-dimensional landscape. And then when you ask a Watershed Transform to execute, it will take all of these pixels and it will grow. And the water level will grow at the same height. So when this is at this height, this will be here. And when the water is at this height, all of these pixels will be red, all of these will be light blue, and all of these will be this darker blue. And these will have converged on an edge. You can keep raising the water level until you have this bright blue, this dark blue, and then the light blue and the red will meet on this edge. So you could see that you could have this convergence. So what happens in this simulated raising of the water level is the markers grow and then converge. So you can think of the Watershed Transform as a region growing tool that converges based on the topology of the landscape function. This is the one-dimensional description. You can also imagine it as a two-dimensional description here. And all of these diagrams show basically the same thing. If you're able to mark in these valleys, which are usually described as catchment basins, as in the nomenclature right here, if you're able to mark in the valley, then all of the pixels in that valley will take on that label. All the pixels in this valley will take on this label, etc. And you're able to converge on these crests or ridges or watershed lines. And that's the basis of the Watershed Transform. Now if we go back and if we look at our image, we see a number of grains. If I turn on the Sobel edge map, let's look at what this actually looks like in a one-dimensional plot. So if I come over and I go back and choose a ruler, let's make a ruler go from here to here. Now I'll double click here and I'll rotate the image just a little bit. Where's my rotate? And what I'm going to do is I'm going to ask the ruler for an edge for a profile intensity. And what we see in this part of the image, I'll just scale this so it's about the same as my figure here. What we see in the image of the grains is I have high intensity grains. Let's actually, all right, there we are. There's the Sobel. So I have high intensity grains, and then it drops off where I have a pore between the grains, and then it drops off between this pore. Now that's the intensity map, but if I look instead at the Sobel map, I can see that right here I'm in a valley. So this is my Sobel, I'm in a valley. Here's a ridge between where I have high intensity edges, and here's actually another little valley that represents the air between these two grains. Here is the middle of this grain. Here's a tiny little valley that's hard to see, and then here is another spot in the middle of the grain. So when you evaluate the Sobel of a map, it creates this landscape function where everywhere you have a boundary, so for example the boundary between this grain and air, or between this grain and air, everywhere you have a boundary, you have this elevated intensity. So if you were able to label these pixels in this valley, right here as grain, these pixels as grain, and these pixels as grain, if you're able to label the pixels in between as air, then they will expand, and all of these will become air, all of these will become grain, and these will become the edge conditions. And that's what a watershed transform does. So in order to compute a watershed transform, you have to have markers. So you have to have markers inside the grains. And so here you see markers inside this grain and markers inside this grain. And you have to have markers inside the air. So you've got markers inside here. And so these will spread right up until this ridge. These will spread right up until this ridge. And you'll have a segmentation that goes right up until the edges. So if I right-click on the multi-roy, I can go all the way down to the bottom and choose watershed transform. And then it prompts me to use a landscape function. So recall that there are two inputs to the watershed transform. There is the markers, which is what we're starting with when we right-click the multi-roy, and there's the landscape. So let me choose the Sobel as the landscape. In Dragonfly, there's an optional third parameter, which we'll look at in the next example. I'm going to set none. Now it's going to evaluate the watershed transform, this approximately 200 cubed pixel data set. So it's going to spread the orange, it's going to spread the blue, and it's going to try and converge on the grain boundaries. All right, so we see what it's done, and so if we hide the edge function, here is a look at our grains, and here's a look at our mapping. So it doesn't do a great job of separating these grains because there were not high enough resolution sampling where we had blue pixels or air pixels. If you did have blue pixels in between those grains, then you would get a good separation. So here we have grains and sometimes the interface between grains labeled orange, and then we have the air labeled as blue. So that's what a watershed transform can do for you. Now suppose we want to do the next step, and that is we want to separate the grains. So in our first example that we just completed, we did the watershed by marking the centers of the grains and the center of the air, and we did a watershed on the edge function, or the Sobel image, as our landscape. Now we're going to do something different to try and separate the grains. We're going to invoke the distance map, or the distance transform. So I'm going to delete that ruler. I'm going to go back to my multiple view and hit reset. Now, I can take my background, so I'm actually going to take this multi-roy, I'm going to extract out the background, right-click, and extract as an ROI. So if I hide and I show this, this is all of my background pixels that are currently labeled. I'm going to create a mapping of and use distance map like we did yesterday. This will create an image where every pixel that is not blue will take on a value that is its distance from the blue frontier, its distance from the nearest blue pixel. This will give us almost what we need for a landscape function for our next watershed transform. And this is going to allow us to try and do an operation which separates the grains. And we're going to see the limitations to this, and we're also going to see some of the differences based on how you choose your seeds. Now, the landscape function that comes out of here will be the distance from the blue, and we're actually going to end up inverting that, and you'll see what I mean in a minute. All right, so if we look at this image, what you see here, we'll turn on the blue for a second. So here are all the blue pixels, and I'll just double click to go full screen. So the pixels that are only one away from the blue have a very dark value. The pixels that are in the center of the grains, they have a very high intensity value because they are far away from any of those interfaces. Now what I can do is I will have to have some seeds for doing this watershed. And I can go to my thresholding tool. I can turn on define range, and we're actually going to use the, let's see if we click here, and I guess maybe it has to be visualized. So let's turn off this and turn this on, and now ask for the distance map. What I can do is I can threshold, and if I threshold, we see now that we have the centers of the grains identified. What we want to do is have the center of every grain identified, but not be connected to another grain. So if we consider these as separate grains, this would be too much connectivity. So there are trade-offs here, because if we have multiple clusters inside a grain, so we could end up getting a grain labeled as 2 grains. So for example, if this pixel is not connected to this pixel in 3D, this will expand as a grain, this will expand as a grain, and so this will be counted as 2 or 3 grains. Now in 3D they are all connected, so it's actually okay. So let's suppose we try this thresholding. So we just have a thresholding set and we add to new. Now these are all of those thresholded grains right here. What we need to do is we need to label each one of these individually, and that is just done by going to connected components and asking for a new, in this case we'll do 26 connected multi-roy. Now when I turn that on, we can see that this is a cluster of one color and this is a cluster of another color. So these are my seed regions that I'll do for a watershed. Now, if we were to look at our distance map in profile, if we look at something like this, then what we see is, let's look just at the distance map. And it seems to not be showing up here. Let's make sure we can select it. There it is. We can see that the distance map goes up in the middle of the grain and then down and then up. This is the opposite of what we want for our landscape function, so I'm actually going to invert the distance map. So I can right click on the distance map and I can go to modify and transform, invert, and I will just tell it to invert the values and apply. So it's much darker, so if I increase the brightness, you can see now that if we were to go, we see now that these are now the valleys of, so it's bright and then it goes dark and then gets brighter and brighter. So this is now the proper landscape function. Now what we can do at this point is we could take this multi-roy, these are all of our grains as seeds, we could right click and go to a watershed transform, and we could do the same thing we did before, but in this case our distance map, our inverted distance map, is our landscape. Now I'm at first going to show you what happens if we don't choose a mask. So if I expand with the watershed, it's going to expand these grains out, these pixels outward, and then they'll converge wherever they converge. So this is what it looks like. So I'm going to show you my grains again and show you my image again, and this is what's happening. But I have all these pixels out here that are not properly labeled. So something somewhere is contributing to that, and this is where we could benefit from actually having a mask. So recall that in this process we created this multi-roy, and therefore we could say when we're expanding these seed regions, let me see if I can click undo on this. And so if I'm expanding this seed and this seed, rather than expanding out until it converges, we could tell it to expand either until it converges here or expand until it hits the limit of the orange mask. So we saw what the results look like when we don't use a mask. Now if I take this multi-roy and I take the grains and I extract that out as an ROI, so this is my grains as segmented by the watershed in the first example, I could use this as the mask. So let's see what happens. If I right click on grains and I do watershed transform, we're going to do exactly as we did before using the inverted distance map as a landscape, but in this case we're going to use the grains from the watershed as our mask. And so in this case it will expand out, but it won't expand beyond the limits of that mask. And so now we'll look at the result. Where's my multi-roy? I don't see my multi-roy. Did I even choose one? I can't find it. Oh, here it is, grains. Grains, and right now it has this nonsense coloring, so let's ask if we could. What we'll do is I'll pull in these grains into my analysis, and here it's going to automatically pull it up with this discrete lookup table. So what we have here is we have the grains and they've expanded up until the air, so they don't expand into the air, or they've expanded until they hit another grain. So this is our separation, and it's separating the grains based on the topology map that comes from the inverted distance map. Now if you look here, this is what happens when you determine your seeds and you have multiple pixels inside the same grain. So if your seed regions are too conservative and too small, then you'll get this sort of artifact, or this sort of artifact you see here. Conversely, if you have seeds that are too big. So in our seed region, we had some pixels from the center of this grain and some pixels from the center of this grain, but they were connected. So they were only treated as one seed. Likewise over here. And these colors are random, but if they're two grains touching each other, it's very reasonable to assume that they're actually the same grain. And if you did a selection here, so if I just selected, then you can see that all of these are the same grain. And oh, these are in fact different grains. So sometimes you can't tell until you either closely look with this tool or with the probe tool. So you can see what happens. You can get over segmentation if your clusters are too small, and you can get under segmentation if your clusters are too big in the seeds. So what we've looked at today is the Watershed Transform, and we've done the two classical implementations, or I should say applications of the Watershed Transform. One application where we're trying to separate foreground from background, and that is we have two seeds, and we use the Sobel, or the edge enhanced image, as the landscape function. The second application is to take already segmented grains, use that to build a distance transform. Then we create seeds where the center of each grain is a different label, and we expand against the distance transform as the landscape function. So those are two different applications, but they're both using the same approach where you're creating some sort of image function that helps you provide a separation or a barrier, and that landscape function is how you evaluate the watershed. All right, with that, I'm going to go ahead and switch over to questions and answers. I'm going to pull up the questions and answers. There are already 4 questions and answers in the queue, so let's see what they are. The first question is, do the markers need to be at the bottom of the valley, or can the markers be anywhere in the valley? That's a great question. They can be anywhere in the valley. They don't have to be at the center of the valley. The watershed will flood everything in that valley at lower intensity. The next question is, well, it was a question that was asked earlier, but from Lars. Having trouble downloading the release. It ends as a partial download of about 1 gigabyte. Just send an email to support. Someone can probably create a new download link for the release candidate for you and send it directly along. I don't think the release candidate is posted anymore. I think it was only posted for 1 week. So if you didn't get it last week, I don't think the link is even available anymore. Maybe it wasn't time limited. Next question, mouse is not synced and screen lags significantly. Yeah, I don't know what Zoom is doing, why some users get to see it in real time with high sync and other users don't. Maybe Zoom is having congestion issues today. Next question, Sydney asks, would it make sense to have a wizard or a basic macro to apply the required sequence of steps for watershed segmentation? I suppose it would, and if you wanted to do watershed segmentation for foreground versus background, there's actually a tool. That's something that is available in Dragonfly Pro for customers that have purchased a Dragonfly Pro. If you create an image, it will automatically create a Sobel for you, and then it will take the Sobel image and it will it will then prompt you for what you need to do to create seeds. I think I haven't used that in a while, but it does create a wizard that allows you to use that. So there is that. You could also create your own macro if you wanted to for doing the Sobel or any other operation. So yeah, it makes sense. It's useful. It's just something that is currently available only in the Pro version. The next question, I've used Watershed extensively, and they often make use of infinite values to force very steep valleys. How would I do that in Dragonfly? I'm not sure I see why that would create a value, but why that would create a numerical advantage on the routine. But if you wanted to do that, you could take your image and you could go into image processing and you could square the image or apply an exponential function, and that would greatly accentuate the high intensity values. I should mention that the output of the Sobel image, I believe, is still unsigned short, where still values range from 0 to 65,000. The output of the distance map is a floating point image where you can have values that approach infinity. So if you're doing it on the distance transform, you could try squaring the image or otherwise applying some sort of mathematical function to accentuate those ridges. All right, those are all the questions we have. I want to thank you for your time and attention. Sorry we did a slight restart at the beginning. I hope that synchronized for most people. This video will be available on YouTube, so you can watch the synchronized version then. And we'll be back tomorrow. Oh wait, we do have one more question. I would like to train a deep learning model using a mask instead of thresholds range, and it is not working. Any tips? Well, the deep learning does allow you to provide a mask as long as you're not using segmentation wizard and you're using the regular deep learning tool. It's not based on thresholds, so maybe if you want to send a more detailed email so we can give you tips on that, because all of that capability is built there into the deep learning tool using a mask. All right, well, thank you everyone for your attention. We'll be back tomorrow and talk about, I guess, cylinder coordinate transforms, or thinking about data in the cylinder space and understanding how users might want to evaluate data there. So thank you all. Have a great day. Stay healthy, and we'll see you tomorrow. Bye-bye.